Okay, so let's finish this off. We've got to do the bending moment diagrams. Now, there's a very, very quick way to get the bending moments for the the first segments of both sides of the beam. So we're talking about this section here and this section here. Okay, so again, you're going to need to know how these things behave under given loading scenarios. For example, for shear force, we know that the first segment of the beam, there's nothing acting, so it's going to stay the same. The point load pushes it down, the UDL drops it down in a linear manner. Now for bending moments, when there's nothing acting, we have a linear thing happening. It's going to be the anti-differentiation of that, or that's the differentiation of a line. So we have a line acting here, and then a UDL is a quadratic sort of function. So I'm going to show you how this works really quickly because we do have a bit of time here. Here's my left bit of the beam. Here's my reaction, 1200. Here's my bending moment, M1. Now you can see, as you can see from this, if I sum the moments about the cut, we can say that sum of the moments clockwise, which is 1200, times that distance of 0.3, which is this distance here, because remember we're coming up with this right up until that point load begins to act. So the distance is 0.3. So it's 1200 times 0.3 in the clockwise direction, and in the counterclockwise direction we just have M3. So you can see that from the left-hand side, the value of the bending moment up until that first point load is the value of the reaction times the distance to the first point load. So if we remember that, this becomes a quick and easy thing to do. I'm going to show you from the right-hand side as well. We have 1670 here. We have a distance of 0.2. And our M is going to be this way. This is our M3. So sum of the moments about the cut equals 0. So we have counterclockwise, we have 1670 times 0.2, and clockwise we have M1. So M1 equals 1670 times 0.2, which is the value of the reaction times the distance to the first point load. So remember that. Put a mental note on that one, please, because here's how we're going to do this really quickly. We're going to say straight away that, well, we know that the starting value of M is always 0. So M1, we're just going to take our reaction, which is 1200. I'm going to times it by the distance to the first point load, which is 0.3. And that gives us a value of 360 Newton meters. And we know that that's acting linearly. So we're going to say, let's call this 100, 200, 300, 400, 500, 600. And this is all in Newton meters, obviously. And this is all in newtons. All right. So at 0.3, our value for M1 is going to be 360. So it's going to be something like that. And we know that it's going to act linearly from 0 up until that point. Done. Now from the right hand side, we can do the exact same thing, because as I just showed, we can say that M3 is going to be the value of the reaction, 1670, times the distance from that reaction, which is 0.2. And that gives us a value of 334 Newton meters. Okay, so if we go over here, that gives us 334, which is something like that. And we know that that acts linearly again up to the 0 point at the end of the beam. Now what happens in between is the somewhat tricky bit. Well, we have an equation that we came up with before for the line. Here it is. There's the equation for the line. So if we anti-differentiate that equation, we'll come up with the equation for the quadratic that acts in the same space. Now, remember, for this equation, x is 0 is starting right there, not here. That's for the beam, but for this function here, for this line, x equals 0 is right there. So the same thing is going to apply for our quadratic. So we could say that, so this is v between 2 and 3. That's this point and this point. So we can say m between 2 and 3 is the anti-differentiation of v between 2 and 3, which is 700x take 735 x squared. Right, I've divided that 1470 by 2 and then upped the indice to 2. So if we were to differentiate that, that would be 2 times 735, which is 1470, blah, blah, blah. You guys know this stuff. Plus something c. Well, how do I know what that thing c is? It's going to be very easy because I know that here's my x equals 0 point. I know what the bending moment is when x equals 0. I know what it is. It is 360. So when x equals 0, we know that m, so m at x equals 0, we could say m at x equals 0 equals 360, is 360, which equals all of that. And when x equals 0, that's 0. That's 0, which means that c has to be 360. All right, so that's 360. So I've already got a function for this quadratic stage here, which means that m between 2 and 3 is this. Now I also know where my bending moment is at a maximum, because that is where the shear force is 0, which is where along the beam it's 0.78 meters along the beam, but from here it is 0.48 meters in, as we figured out before. So my x value is going to have to be 0.48 in here. So all I'm going to do is I'm going to say m at 0.48 when x equals 0.48. I'm going to substitute 0.48 into this equation mathematically, and it's going to look like this: 700 times 0.48, take 735 times 0.48 times 0.48, plus 360. 526 or 527, we'll call it 527. 527 Newton meters, that's my maximum. So I'm going to go to 527, which is something like that, and it's acting at 0.48 from that point, which is 0.78 from the start. And now I know it's acting quadratically between these points, so I draw a quadratic, just like so. And take a bit more care than I did, but that is us done. I hope that helps. I hope that makes things easier for you guys. We're just using this diagram here to come up with simple equations with a couple of cheats in there. Remember to calculate the bending moment at this point up until that first point load is going to be the reaction times that distance. And same from this side, 900 times 0.2. Here it's 1200 times 0.3. So a couple little shortcuts for you guys. The bending moments are a little bit trickier, a little bit, I guess. Shear force is very easy. You must know how these things behave under given loading scenarios. But we've talked about that enough. I hope this helps. Much love. Goodbye.